Hi everyone, this is Bharat Mupasani, a PhD student in computer science from University of South Carolina. Today I'll be presenting my paper, a dataset and baseline approach for identifying usage states from non-intrusive power sensing with MIDAS IoT based sensor. The outline of my presentation is as follows. I'll be talking about the motivation of our work followed by data collection and the dataset, which is a crucial contribution of our paper. Next, I'll introduce you to the state identification problem that we tried to approach in our paper, followed by baseline results that we have obtained and contributions and references. When it comes to power-based analytics, majority of the existing literature work focus on power forecasting, which helps the end user to understand his power usage pattern. Anomaly detection in the power usage is also one of the major works, which is basically an alerting system helps in identifying unusual power usage patterns. Some other works are based on non-intrusive load monitoring, which is a disaggregation of aggregated power usage to understand individual appliance load. Apart from these, traditionally, the malfunctions in the system like machine faults are analyzed as a vibration data in a technique called as condition-based monitoring. But this is expensive and intrusive in nature, which is not appealing to an industrial setting. When considering an industrial environment, it becomes important for an end user to understand what is the state in which the industry is in given a working scenario. In an electrical system running on AC frequency, any perturbation in the system manifests as an energy spectrum. The signature of the system reflects the state in which the system could be. Some of the examples of a state can be a factory floor with all the machines running normally, or a machine beginning to fail. In a data center or an office, the system under heavy load can be considered as a state. In an industry, an unusual load that the system has not seen till now can be a state as well. It becomes important to tackle this problem for the end user to manage his system efficiently. In our current research work, the power data that has been used is being collected by the MIDAS IoT sensor from TANTU4. The sensor measures all the crucial electrical parameters like electrical current, voltage, active power, power factor, etc. at a sampling rate of 300 milliseconds. The device is also capable of collecting three-phase current and voltage harmonics from 2 to 32 harmonic levels, along with total harmonic distortion at sampling rate of 500 milliseconds. The electrical consumption data given by the MIDAS sensor has 28 features, and the harmonics data has 193 features in total. Currently, the sensor has been installed in 8 different locations spanning across different industries like manufacturing, hospital, and education. On the rightmost column of this dataset table, you can see the figures showing a one-day power usage pattern for all the industries. We can see the varied nature of power usage pattern of these 8 different industries. We have released for the research community the electrical consumption data and the harmonics data for a span of 15 days for each of these listed locations. We have used the India 4 location data to illustrate our baseline approach in our research work. Coming to the state identification problem, the objective of the state identification problem is to identify power usage patterns of any system, like buildings or factories of interest. Formally defining the state identification problem, let us say we have a list of selected features F that the sensor is able to capture. You can think this as the columns of the dataset, which are different parameters. Also, let us assume we have X be a collection of power usage observations for a location at a known interval delta. This can be viewed as rows of timestamps. Now, the state identification problem is to produce a function f which maps these real numbers to an integer from 1 to k. Let us talk about what is k in some time. Now, when s is equal to f of x, the state corresponding to x, that is a collection of power usage observations, is a number capturing the category assigned to those observations. This can be understood as mapping a set of observations or power usage patterns to a categorical number, in turn identifying different power usage patterns based on their numbers assigned. These numbers can be called as different states. So here what is K? In our work, we are interested in unsupervised state identification problem. That means we don't know how many different states are present in a given data. The number of state is also to be learned. To address the state identification problem that we have mentioned earlier, in our baseline method, we have used electrical current harmonics data as our featured dataset. The next step is to find optimal number of clusters in this selected dataset for a selected time period. For this, we have used K-means algorithm along with the elbow method on the training dataset. In the next step, we have trained a classifier with the electrical current harmonics data that we selected earlier and the states obtained from the clustering algorithm from the previous step. For this, we have selected random forest classifier. Now, the trained classifier can be used on a new test data to classify different observations into their respective states. In the below figure, you can see different power usage observations being classified into different state categories by the classifier. Here, it has been shown with timestamps on the x-axis and active power on the y-axis. Each observation is given a different color with respect to their states. In this specific date, the classifier found that there are 5 different states. As the selected electrical current harmonics data is a high dimensional data, visualizing these different states would be difficult. For this purpose, we have used principal component analysis to reduce the dimensions of our data into 2 dimensions and viewed the obtained states. Here, the x-axis and y-axis are the 2 principal components that we obtained from the PCA algorithm. We can see these different states being clustered into different groups. Upon validating with the end user, these identified states for different observations at a given time period are identified as different operating scenarios of the industry. We have released our dataset following the FAIR principles. In the following GitHub, you can find a clear documentation of how to obtain the dataset along with code and other resources that will help you in understanding the dataset. The GitHub also contains the metadata explaining the 2 different datasets that are being released. We also uploaded our baseline results on all the released datasets. We also released the results of our baseline approach on all the released datasets. These results can also be found in the following GitHub. Additionally, we have released the data that has been used in our research work and also the code that we have used in our research work so that it can be used to replicate our results. Once the user comes up with a different method for tackling the state identification problem, he can validate the results of the states identified following the documentation in our GitHub. We have provided the summary of states identified using our baseline method along with the centroid details for the each state identified using our baseline approach. In this paper, we presented a rich data set of power consumption spanning 8 locations in 3 different industries: manufacturing, education, and hospital, and 2 countries, India and USA, for a period of 15 days. The power data that is being released is collected by Midas sensors from Tantiford. We release the datasets following the FAIR principles and with a clear documentation in our GitHub to obtain the datasets. We introduced and described a generic state identification problem that is much of interest to the industry. We describe an initial unsupervised machine learning based solution to extract different operating states of the power load for a location using current harmonics that can serve as a baseline to the community to accelerate research in this area. These are the references that we used in our research work. Thank you.